it will be more about temporal trends, and it's Luc Miaz from ACIS, Stockholm University, that will present. And the title is Temporal Trends of PFAS and Fluorine Mass Balance in Pooled Serum from First-Time Mothers in Uppsala. Welcome, Luc.
Yes. Thank you. Thank you for the opportunity to present our work today. So in my talk, I will present the result from our study published this February in Environmental Science Processes and Impacts. So first, I will give a few words on the method we used in our studies, and I will discuss the result from the three parts of our workflow. The target screening, where the compounds analyzed are quantified, the extractable organofluorine and suspect screening, where we try to assess the presence of other PFASs, and finally the non-target screening, where we try to identify emerging features. So with the method, I will discuss the samples and method we used in our study and try to keep things quite simple. But first, I will give a few words on the tap water contamination that occurred in Uppsala, because that's where the women from the cohort we studied are from. So in Uppsala, Uppsala is among the cities that were exposed to contaminated drinking water. The source is suspected to be the military airport of Erna, specifically the firefighting foam with hexane sulfonate that was used until 2003. This contamination is sustained with evidence from extensive studies on human serum from the POPUP cohort, which consists of first-time mothers from Uppsala. The serum samples analyzed from 1996 to 2016 showed a decrease in concentration of hexane sulfonate since the closing of contaminated wells in 2012. However, it remains unclear if the exposure is fully characterized due to limited number of targets. We analyzed 57 samples, serum samples from the POPUP cohort that ranged from 1996 to 2017. These were pooled serum samples from several individuals. We had 3 pools per year with different numbers of individuals in each pool, but a minimum of 6 people and up to 25, and in median 10 individuals in each pool. The ages of the women in the cohort range from 19 to 41, but in average they were around 29 for all year. And there were other studies conducted on the same cohort, but the pool composition for these studies study are different. We had quality control samples, certified material, as well as blanks too. The objectives of the study were to extend the time trends for non-PFAS in the POPUP cohort up to 2017, then carry out a fluorine mass balance to assess what the fraction of the fluorine in the cohort is accounted for by PFAS, by non-PFAS, and then to carry out non-target and suspect screening to identify novel PFASs that were not captured by the targeted methodologies. Just to give you a hint of what the extraction method looked like, it was an acetonitril extraction followed by an analysis of the compounds using newly developed UHPLC Orbitrap method. So I will just bring you through this diagram, which shows the extraction procedure. So we started first by dividing the putting half a milliliter of serum for all the 59 samples, along with quality control NIST and blank vials. The sample were spiked with a mix of labeled internal standards to account for the losses of the different targets analyzed during the extraction process. And then we added 4 milliliter of acetonitrate to the vials. They were then mixed for half a minute, sent to a nutrasonic bath, centrifuge, and then we took the supernatant of extract and transferred it to a new vial. It was repeated twice, and the supernatant were put together. Then we concentrated down the supernatant to about 1 milliliter under a stream of nitrogen. We prepared new vials with carbon and acetic acid in it. Then we transfer the milliliter into these new vials. Then we mix them, centrifuge them, and then transfer what's liquid in it into new vials. We add recovery standards to account for the losses in the internal standard. And then we transfer that to vials that can be analyzed with the LC-MS. For the quality control assessments of the target PFASs, we perform a spike recovery experiment. And it showed that the method had excellent accuracy and precision. The recovery were between 70 and 150 and 30 with some exceptions. Our method showed good consistency with previous studies and certified values relative to the analysis of reference material from NIST. We also compared the Orbitrap method to existing triple quad method and found consistent results with better performance using the Orbitrap. The quality control for our method showed low blank concentration, typically below the limit of quantification. After the extraction procedure, we performed the analysis of the sample on a UHPLC Orbitrap. That is, we used a chromatograph to separate the ions in time and a ultra high resolution mass spectrometer to analyze the ion mass charge ratio. The Orbitrap was set to a full scan data dependent MS2. This means that we had a list of masses for our targets analytes and for a few hundred of suspects that when their mass was detected would trigger fragmentation. That is, some of the ions at this mass would be sent to a collision cell to be fragmented. And this allows to later confirm the identity of our targets and possibly infer the identity of the suspects. Our method is thus designed both for target and non-target screening. So on the right, you see a small animation of the procedure in the mass spectrometer. The ion beam is directed using quadruples, leaving positive and neutral molecules out. Then the ions are sent to the detection cell, and the oscillation of the ions induce a current that can be used to infer the mass charge ratio using a Fourier transform. And as I said, we have a list of suspects on target, and when a mass is matched, when it's detected, then some ions are sent to a collision cell, fragmented and sent to the detection cell. So we have their mass. And the method for fluorine mass balance had a similar extraction procedure described before, but without the addition of internal standards. The samples were analyzed on a combustion ion chromatograph using a previously reported method. For the measurements of total fluorine, we added 150 microliter of serum that were combusted at 1100 degrees under a flow of oxygen and argon for 5 minutes and injected to the ion chromatograph. For the assessment of accuracy and precision of the total fluorine data, we had replicate standard reference material analyzed. The samples for the analysis of extractable organofluorine were prepared together with blanks and spiked sample. The EOF concentration in the samples were recovery corrected by dividing each value by the average PFAS recovery measured for spiked sample by CIC. Finally, the total known extractable fluorine concentration was obtained by summing the fluorine concentration from all individual PFAS. I will now present the trends we observed for our targets analytes. Mainly, we found declining trends for most compounds, in particular for longer chain perfluorinated carboxylic acids. Among the PFCAS, so the perfluorinated carboxylic acids, for which we had a temporal trend analysis done, all but the hexanoic acid and branch PFOA displays statistically significant upwards then downwards trends with a p-value below 5%. The declining trends in PFOA from 2002 and earlier likely reflect the 2002 phase out by 3M, so the main producer of PFOA. Previous studies on the cohort, which had not been analyzed samples up to 2017, had observation that suggested a steady increase throughout the period. However, the latest samples analyzed in our study show a decline in recent years, also for longer chain PFCAS up to PF3DA. But the change point for C9, C11, and C13 PFCAs around 2009 also indicate that exposure sources of these PFCAs have been restricted, but the delay relative to PFOA suggests that regulation of these substances occur later than PFOA. For perfluorinated sulfonic acids, we observed significant upward and downward trends with also a p-value of 5%, at least for many of the PFSAs. For instance, we had PFBS with a change point in 2007. Linear and branched hexane sulfonate had change points in 2010 and 2011. And branch and linear PFOS had change points in 2001. The declining concentration of hexane sulfonate in 2011 highlights the effect of mitigation efforts on exposure to PFAS via drinking water in Uppsala. In contrast, the PFOS change point in 2001 is consistent with that of PFOA and likely reflects the phase out of perfluorooctane sulfonic fluoride-based substances in the early 2000s, which is also reflected in the rapid decline of PFOS precursors, namely FOSA, MEFOSA, and EDFOSA, throughout the study period. So in summary, we observed a decrease in concentration of most our target compounds, in particular long-chain PFCAs, either for the whole time period or since or around 2010. I will now talk about the result for the fluorine mass balance and the suspect screening. We were able to identify another feature in our sample using suspect screening. Extractable organofluorine was above the method detection limit only in a third of the samples. This hampered comparison to total fluorine and to the fluorine from target PFAS. Some observation could be made, however, by focusing on samples with detectable level of EOF. Among these samples, the proportion of EOF explained by target PFAS ranged from 11 to 75%. We observed significant declining trends in total fluorine and in the fluorine from target PFAS, and about 4% for both. 4% decline per year. The sample collected in more recent years have a larger fraction of unknown EOF compared to older ones. And the percentage of total fluorine accounted for by EOF also increased significantly at 2.2% per year, indicating that collectively known and unknown PFASs make up a larger percentage of the total fluorine in most recent years. During our initial examination of the suspect screening data, we matched a total of 5 exact masses with 5 ppm mass error to suspects in our database. However, given the overall low PFAS concentration in the target population, all 5 suspects were ruled out after MS2 inspection, so the data from the fragmentation of the ions. A follow-up investigation of our suspect string data using lower peak thresholds revealed the presence of an exact mass and a MS2 spectra corresponding to PFAS. We confirmed the assignment using a standard of PFAS from Wellington Labs and running it together with a serum sample. The summing quantitative concentration for PFAS range approximately from 0.06 to 0.28 nanogram per gram, which would contribute at most to 0.25% to our prior known EOF estimates. However, these estimates require confirmation using a method validated for PFAS, that has a spike recovery experiment. This highlights the value in collecting non-data and suspect screening data that can be retrospectively mined. Indeed, with PFAS databases, the data set collected can be continuously reprocessed without reanalyzing samples. The savings in terms of cost and time associated with retrospective mining compared to reanalyzing each sample represent a considerable advantage for non-target and suspect screening workflows. Our data builds on the initial discovery of PFAS in human serum from Sweden by Weiss et al., who showed that human exposure to PFAS occurred primarily during the 1990s and early 2000s,
Luc,
and has been declining since
just want to say 5 minutes left, okay?
Yep.
So, thanks.
Yep. So PFAS was also detected recently in water sample from the Baltic, in fish and surface water from Canada, in water sediment and fish from China, and in water and straw from the high Arctic. PFAS was used as an erosion inhibitor in aircraft and was phased out of production by the 3M company in 2002, along with PFOS and other perfluorooctyl-based substances. The phase out of this product appears to align with our observed time trends in human serum from Sweden. Finally, regarding the non-target screening, I will describe our workflow and our main results. We approached the non-targets with two strategies, both looking at breakpoints in 2010 using a custom-made algorithm based on a show test. We tested the performance of the algorithm on synthetic data generated for a combination of increasing, constant, and decreasing trends, and found overall good performance. The first strategy A, consisted in matching trends to hexane sulfonate, and strategy B consisted in matching increasing trends after 2010, which we hoped could suggest replacement compounds and possible emerging concerns. The diagram on the right illustrates our selection process for strategy A. We performed a show test on all 1,400 features detected to determine if a breakpoint in 2010 was significant. For those 400 and so features, we assessed if the trends were the trends before and after 2010 corresponded to the trends for hexane sulfonate. And finally, we filtered the 18 resulting feature from strategy A and matched 4 target compounds, namely PFBS, PFNA, PFG, and PF3A, as well as 3 additional features for which we had unfortunately no MS2 data. One of these 3 matched with a chlorine isotope pattern, but we have no confirmation. Strategy B filtered with higher correlation coefficient than the strategy A, yielded 7 features of interest. Both strategy highlighted features that would need further investigation. Well, I forgot to move that. So, in conclusion, we observed declining trends for all PFAS, including the longer chain PFCAS we analyzed, in particular PF3DA, and this is not frequently reported. On the mass balance side, we observed significant decrease in total fluorine. However, no trends emerged for EOF, but we found a significant increase in the fraction of unknown extractable organofluorine, and this is consistent with with previous research. The full extent of exposure to PFAS is not captured, and using a suspect non-target screening approach, we were able to detect in our samples PFAS and several unknown features, which should be included in future studies.